Hello everyone and welcome back to Nunley Math. Thank you so much for joining us here today as we look at the quadratic formula. Now this is the last video lesson my students are going to receive this academic school year. As I've mentioned several times, I do make these lessons primarily for the students that are in my classroom as a learning resource and a tool for them, but we are certainly thrilled that many of you have chosen to learn along with us as we have done that. I especially want to give a shout out to the 12 viewers from Ireland who popped in on us this last week. Very excited and thrilled that you chose to join us. Please continue to watch, and if you get an opportunity, let us know with a thumbs up if you're learning some things that are of use or value to you. Now, today we are going to talk about the quadratic formula, and this is really one of my favorite lessons to teach because the quadratic formula ties together so many different topics that we've talked about during the school year, and when you first approach it, it really seems very daunting and overwhelming, but if we can take our time, make sure we understand how the formula is used, where the formula comes from, then it's really going to save us a lot of time and effort long-term in mathematics. So it's going to start off seeming really complex, but once we understand where it comes from and what it's for, it becomes very simple and very useful for us very quickly. So here's what we're going to do. I'm going to go back and review with you for just a second the different ways that we have discussed to solve quadratic equations. Method number one, we learned that we could solve quadratic equations by factoring, and we actually learned several different ways to factor a quadratic equation. We learned about how to factor out GCFs. We learned about the difference of squares pattern. We learned about the binomial squares, or sometimes we refer to them as trinomial squares patterns. We learned about the guess and check method. We learned about solving by grouping, and then we discussed the fact that if none of these types of factoring worked, we would have to describe our quadratic equation as being unfactorable. Notice we don't say that it doesn't have a solution, we just say that that solution cannot be found by factoring. If you're uncomfortable with those ideas, we certainly have several lessons on factoring. I would encourage you to go back and check those out again, just to make sure you have mastery over those before you end this course. Then, we talked in our radicals unit about the fact that a lot of these unfactorable quadratics were actually solutions that gave us irrational numbers, or numbers that go on and on forever and ever without ending or repeating. Typically, if we can factor a quadratic equation, it means that we've got some really nice, neat, rational numbers, numbers that can be written as fractions. But if they are unfactorable, usually it's because the numbers are really difficult to just guess and check our way through. It means they go on forever and ever without ending or repeating. But we came up with several strategies for how to deal with those. The first, we said, if you've just got a single x squared, an ax squared equals b pattern, a lot of times we can just divide both sides by a and then square root both sides. We talked about the fact that if we have something of the form x plus a in parentheses and the whole side is squared, we could also square root both sides here and solve the quadratic. And then we talked in our last lesson about completing the square and how if we are not fortunate enough to be given one side as already a binomial square or trinomial square pattern, we can use completing the square to help us figure out the solution. So let me just walk through a couple of these very quickly. For example, if I were to give you 3x squared equals 49. You'll notice that that fits this pattern down here, this ax squared equals b. And in the lesson 2 days ago, two lessons prior to this one, we talked about the fact that really we can use the property of equality to get rid of that times 3 by using division. We know that 3 divided by 3 is 1, making this 1x squared or just x squared. And then I mentioned in the previous lessons that I tend to prefer to work with improper fractions rather than mixed numbers, especially early in the problem. If I want a mixed number answer, I will not change it to a mixed number till the very end of the problem because typically those are harder to work with. Once I have one side as a perfect square, we know that the inverse operation of squaring is square rooting. And so I'm going to square root both sides. The property of equality says I can do whatever I want as long as I do it on both sides. And then I mentioned several times that if you are going to have a square and a square root, we know they undo each other, but whatever's inside has to come out as a positive. And then we discussed how that can be written as an absolute value, and then the absolute value essentially breaks down into giving us this positive negative sign. If that's uncomfortable for you, you're going to want to go back and watch that in our radicals unit. Suffice it to say, since this is a review, we're just going to accept that this is true. Squares and square roots undo each other. So we have x equals plus or minus. Remember, I can't leave a fraction under a radical. That's considered to be a non-standard way of writing things, or not simplified. So I split it into radical 49 over radical 3. Now, this violated the rule that we cannot leave fractions under a radical. This violates the rule that we're not allowed to have an irrational denominator. No square roots, no radical signs in the denominator. So to get rid of this, we would have to rationalize it. The way we do that is we go ahead and simplify the 49, make it into a 7. To get rid of this radical 3, we're going to multiply by radical 3 over 3. Now, I picked this number for two reasons. Number one, anything over itself is equal to a 1, and the identity property says I can multiply by a 1 anytime I want. I knew I should use the radical 3 because it matches what's under the radical over here. Radical 3 times radical 3 is going to give me a radical 9. The top is going to be 7 radical 3. So you get 7 radical 3 over radical 9. And then, of course, the square root of 9 is a 3. Notice I left this in fraction form. Dividing by 3 is the same as multiplying by a third. So you could have 7/3 radical 3 if you wanted. Also, don't forget that negative 7/3 radical 3 also works. Hopefully that's a good refresher. Again, if you're struggling with that, you need to go back 2 videos and watch the solving quadratics using roots lesson. We then expanded that and said, if you have a binomial squared, well, you can do the same thing. Squares and square roots undo each other, so these are going to go away. Don't forget your plus minus sign. So I'm going to square root both sides. Squares and square roots undid each other. Radical 18 is 3 radical 2. Again, keeping track of my plus minus sign. And to get rid of this minus 8, I'm just going to add 8 to both sides. Notice I put the positive 8 before the plus or minus 3 radical 2. This is considered to be a standard notation. We always put the rational part before the irrational part. The other reason for that is if I had a plus 8 over here, sometimes it's hard to tell whether the radical is covering the 8 or not. So it's easier just to write it first. Remember, this is 2 answers. In order for us to solve this, we would have to use a calculator to estimate radical 2, then multiply by 3. And whatever answer that is, it's going to be 8 plus that number is one answer, and 8 minus that number is the other. X squared minus 20x plus 36 equals 11. So I look over here and I ask myself, x squared minus 20x plus 36. I don't think this is going to factor, but it is definitely not a trinomial squares pattern, because if I'm using a trinomial squares pattern, this is a perfect square x, this is a perfect square 6, the middle number should be 6x doubled, and it's not. So here's what I'm going to do. I'm going to use completing the square to force this to be a trinomial squares pattern. And I do that by getting rid of this 36 using the property of equality. And then I have just the quadratic term and the linear term over here on the left. And I want to know what the constant term is going to have to be to make this a trinomial squares pattern. Notice, whatever that number is, I need to make sure I do it on both sides, because the property of equality says you have to do it on both. Now, I would put a little star here because, as I mentioned in the last video on completing the square, the biggest mistake people tend to make on this is they tend to add the number on the left side, but forget to put it on the right. When I look at this, I'm going to take the x, or the x squared is going to be x. The middle needs to be half as big. So the middle here is going to be 10x. Let me grab a pen and write that. This is 2 times 10 times x. Now, I know the x is the square root of x squared. I know the 2 is because it's doubled. The 10 tells me that this number is going to be a 100 because 10 squared is 100. And I add it to the other side, and I'm going to simplify the right. Notice this is a perfect square, x squared. This is a perfect square, 10 squared, and the middle is 2 times the 10 times the x. I take the square root of the 100, it's a 10. That's the binomial x plus 10 times itself. Now this one works just like the one over here in example B. To get rid of the square, I'm going to square root both sides. Remember, squares and square roots undo each other, so those are going to go away. Make sure you don't forget your plus minus sign. And then to get rid of that minus 10, I'm going to add 10 to both sides, giving me 10 plus or minus 5 radical 3. Keep in mind, a lot of people tend to try and add the 10 plus 5 or the 10 minus 5. You can't do that because order of operations says you have to do this multiplication first, and we can't multiply that together without rounding it or estimating it because radical 3 is an irrational number. One last one of these, and then we'll move on. If I gave you 2x squared plus 5x equals 18, remember, we want our leading coefficient to be a 1 in order to complete the square. So what I'm going to do is I'm going to divide both sides by 2. I think in most of my examples I've multiplied both sides by a half, but remember multiplying by a half and dividing by 2 are the same, and it was getting a little crowded up here, so I decided to write it this way instead. And I get x squared plus 5 halves x plus 9. Remember, all of these have to be divided by 2. Now, I do have my quadratic term, my linear term. Over on the left, I have my constant over here on the right. I want to complete the square by asking myself, what would I need to put here in order for this to be a trinomial squares pattern? Well, I'm going to cut the middle in half. That's 5/4. 5/4. So this is 2 times 5/4 times x. Well, I know where the x comes from. It's the square root of x squared. 5/4 must be the square root of this number. What is 5/4 squared? Well, hopefully you came up with 25/16, which we add to both sides. Now, probably a lot of you are not liking this at all because we don't like working with fractions. However, sometimes it can't be helped. There really isn't a better way to do this if we're trying to complete the square. The nice thing is, once I've made it this far, I know that the square root of x squared is x. I know the square root of 25/16 is 5/4, so I know what my binomial is going to be. Notice over here, I had to take my 9 plus 25/16. A lot of you are going to be tempted to make that into a mixed number. I'm going to go ahead and tell you that mixed numbers are usually harder to work with. What I would suggest to you is that you make 9 into a fraction over 16, and I believe that's 144/16. Now that your denominators are the same, you can add them together and get 169/16. I'm going to back that up. A lot of marks on here right now. Since it's a perfect square on the left, I'm going to go ahead and square root both sides, remembering that squares and square roots are going to undo each other, and I have to keep track of the plus minus sign. That puts me at x minus 5/4 equals plus or minus. This is a perfect square, 13. This is a perfect square, so I went ahead and made it into 13/4. To get rid of the minus 5/4, I add 5/4 to both sides, giving me 5/4 plus or minus 13/4. Notice I didn't write in the plus 5/4. I would typically write that in, but things are getting crowded, and I wanted to make sure I was able to fit everything onto the slide. So I would add those together, and of course you're going to show your work. Here's what's cool about this. This is two answers. Remember, it's 5/4 plus 13/4, and it's 5/4 minus 13/4. When we add fractions with like denominators, we just add the numerator. So 5 plus 13 is 18/4, which simplifies to 9 halves. 5 minus 13 is negative 8/4. Negative 8/4, of course, is negative 2. Whew. That's exhausting, isn't it? Completing the square is a really, really long and drawn out and complicated process. I have yet to find very many students that enjoy completing the square, particularly because you end up with some really messy fractions sometimes, and a lot of times those messy fractions don't come out nice and neat as perfect squares. Instead, they come out messy, irrational numbers, and it just makes for a really long, drawn-out, difficult process. That brings me to my final method for solving a quadratic equation. And if you remember the title of this section or the title of this slideshow, that is the quadratic formula. So here's what we're going to do. We're going to take a quadratic equation in standard form. Notice this is the standard form of a quadratic equation that we memorized. Ax squared plus bx plus c equals 0. And we're going to solve this for x. Now, it's going to be a lot harder to solve for x because there are no numbers for us to manipulate. We're going to have to do everything with just variables, but we're going to follow the same process we used when we were completing the square on the previous slide. Now, you need to know that I am well aware that this is challenging and complicated and confusing. Okay, so this slide in just a few minutes is going to get very full and very overwhelming. However, it's extremely important that you realize that the quadratic formula that we're going to use is not something that I just made up. It's not something that math teachers just invented out of nowhere. There are reasons this formula works, and it's all based on the math that you've learned up until now. So if you find yourself struggling, please don't be surprised. Don't be too hard on yourself. I would, however, recommend that you go back and watch the video a second time if you're having a hard time, because it is important for you to understand what I'm doing here. I'm going to have to go ahead because this is a video. I don't want this to get overly long, although it may be too late. That ship may have already sailed. But I do want to walk through this as quickly as I can. Just know that you might need to pause and think about what I'm saying at certain intervals. So, if I'm looking at this and I don't know if this is a trinomial squares pattern or not, in order for me to work with this equation, I'm going to do it by completing the square. That means I'm going to take the linear term and move it to the other side. I'm going to take the constant term and move it to the other side. I want the quadratic term and the linear term to stay where they are at. Hopefully that was not overwhelming. We just used the property of equality. If I want to complete the square, you will remember I told you it is much more difficult to do this when your leading coefficient is not a 1. This might be a 1, it might not be a 1, I have no idea. So at least for now, I have to assume that it's not a 1 and I need to get rid of it. Ordinarily, if it was a number like 3, I would multiply by the reciprocal, multiply by 1/3, and that would make the 1. Or I would divide both sides by the 3, and that would do the same thing. Multiplying by 1/3 and dividing by 3 are the same. If this was a 5, I would multiply by 1/5 or divide by 5. Since I don't know what number that is, if I want to get rid of a times a, I'm going to have to divide both sides by a. Now, here's where things start to get a little messy. A divided by a is going to become a 1, so that I'm comfortable with, ax squared. But I can't actually do b divided by a because I don't know what that number is. I can't actually do negative c divided by a because I don't know any of the numbers. So instead, I have to leave it written as a division expression. B divided by a, negative c divided by a. Everything got divided by a. Now, it looks a little messy, but we haven't done anything new or unusual. We use the property of equality to get rid of the constant term. We divided to get a leading coefficient of 1. Now, once we're at this point, I'm going to complete the square. That means I need to make it so that this is a perfect square, this is a perfect square, and this is 2 times the roots. 2 times the roots. Notice this is x squared. That's easy. The question is 2 times what gives me b over a? That's tough. 2 times what gives me b over a? It's actually b over 2a. And I know that because if I were to multiply these together, the 2's would simplify, leave me with just the b over a. So b over 2a is what gets squared to go in that blank. Now, to me, that is the most difficult part of what we're doing here, is what I just said, figuring out this number. It goes back to the fact that this is 2 times the roots, x being the root of x squared, and then trying to figure out what this number is. Sometimes you got to play with that just a little bit. That is a little bit difficult. But know that whatever it is, you have to do the same thing on the other side. Next up, I'm just going to clean this up a little bit. This is a little messy. This is a little messy, so I'm just going to go ahead and take this and square it. B over 2a squared. The b squared is going to be b squared. 2 squared is going to be 4. A squared is going to be a squared. So I just write that here. I've just squared this. I also do the same thing on the other side. That's just a little properties of exponents work there. Here's what I know. I know this side is now a trinomial squares pattern, and I know that this side is 2 fractions added together. I'm going to clean up this right side first. In order to add these together, my denominators need to be the same. So I need to know, what do I need to multiply this first fraction by to make it match the second? Well, let's see. This one has a 4 in it. I don't have a 4 over here. This has 2 a's. This only has 1. So this is going to need a 4 and an a. So I'm going to multiply this first fraction by 4a over itself. Remember, 4a over 4a is a version of 1. The identity property of multiplication says I can multiply by a 1 anytime I want, and it doesn't change my answer. This is 4a times negative c, that's negative 4ac, and this is going to become 4a squared. Whew. Again, all I've done is multiply those together, and then now these denominators are the same, so I can add them together. Negative 4ac plus b is b squared, and of course I put b squared first because so I have b squared minus 4ac, or negative 4ac plus b squared, and I'm going to go ahead and put the b squared first. I think it's going to be less confusing that way. Let's deal with the left side over here. I know this is a trinomial squares pattern. I know that we're going to have a plus sign in the middle. I know it's going to be an x plus whatever the root of this is. This is x plus b over 2a squared. Remember, b over 2a is what we squared in the first place to get that number. You've done the hardest part. You're almost done. How do I get rid of a square? Well, square root both sides, just like we've done all along. Squares and square roots will undo each other. Don't forget your positive negative sign. That brings us here. How do I get rid of a plus b over 2a? Well, I'm going to subtract it from both sides. Again, ordinarily, I would write that out. I would write minus b over 2a on this side, and I would write minus b over 2a on this side, but it was getting kind of tight on room, and so I wanted to make sure I got this all in one slide for you, so it looks something like that. Notice here you have like denominators, so we're going to add or subtract fractions with like denominators, which means I'm just going to add or subtract the numerator, and that takes us here. Remember, when you add and they have like denominators, the denominator stays the same. That's how I get my 2a. Whew, that's overwhelming, right? So, this is the quadratic formula. What a messy and involved and challenging and difficult process to get there. Just know, very few students in high school have to do this more than once or twice. It's important you understand why it works. It's important for you to understand that this formula is just the standard form of a quadratic equation rearranged using all variables. The reason we do it with all variables is because this is going to work now no matter what number is in the B or the A or the C position. Does that make sense? Okay. Here's the most important part. You don't necessarily have to memorize this or do all of this over and over again. I need you to have a general understanding of it, but I'm not going to ask you to do this multiple times. Instead, you need to memorize this. And if you were a student in my class, that would actually be a question on your test. Please write the quadratic formula from memory. You need to know this, know this, know this. Hold it in your heart, near and dear to you, because this is going to save you a lot of trouble. So what I'm going to do is I'm going to show you some quick examples of how we can use the quadratic formula and how it's less confusing than some of the other methods. So here's what I'd like to do. Let's say I ask you to solve x squared minus 10x plus 23 equals 0 using the quadratic formula. Okay? Now, in real life, if somebody just gave me this problem, I would probably try and solve it by factoring first, but you're going to find that this would be unfactorable, because if I tried to factor by pulling out GCF, difference of squares, trinomial squares, guess, none of those are going to work. And you might spend a little bit of time trying that out. But because it's irrational, I'm never going to get the solution simply by factoring. I could do this by completing the square, but that's a little bit tedious. You're probably going to like this method better. What I'm going to do is I'm going to take my quadratic formula and I'm going to copy it down. I copy it down for 3 reasons. Number 1, it helps me to remember it. Number 2, it helps the people reading my work to understand what I'm trying to do. And number 3, it keeps me from making careless mistakes. We always, always, always rewrite our formula. And then I'm going to come over here to this equation and I'm going to say, well, if ax squared plus bx plus c is the standard form of a linear equation, of a quadratic equation, then in this case, the number in front of x squared, my a, is the number 1. Remember, there's always an implied 1 here because 1 times anything stays the same. The number in front of x, or my linear term, is negative 10. Keep in mind, the pattern says it has to be plus bx, so this would be plus negative 10. And the number in the c position is 23. Once I know those, I'm going to plug those in to the quadratic formula, like this. Notice, b is negative 10. The formula says use the opposite of b. Since b was negative 10, I'm going to do the opposite of negative 10, plus or minus b again, negative 10 squared, minus 4 times whatever's in the a position, that's the 1, c is the 23, over 2 times 1. I'm just going to plug those numbers in. And then I'm going to simplify. Negative is going to give me a positive. Negative 10 squared is going to be a positive 100, minus 4 times 23 is a 92, and 2 times 1 is 2. I'm just going to simplify, and then I'm going to keep following order of operations. 100 minus 92 is an 8, and then I look at this and I see that 8 is an irrational number. That makes sense because we assumed we were going to get an irrational answer, but 8 is not in simplest radical form. In simplest radical form, it's 2 radical 2. So my answer is going to be 10 plus or minus 2 radical 2 divided by 2. Since both of these are divided by 2, I'm going to take 10 divided by 2 and get 5. And I'm going to take 2 radical 2 divided by 2, and I'm going to get a 1. This is 5 plus or minus 1 radical 2. And that's all I can do without estimating what radical 2 would be and rounding it off. Notice, it's a lot of writing, but conceptually, all I've done is plug in numbers and simplify. You're probably going to find that to be a lot easier than all the logical, mathematical logic or algebraic maneuvers you have to make in order to complete the square. That's why most people like this a whole lot better. But it only works if you take the time to memorize the formula and if you're careful when you're setting up the problem and working it out. Probably you're going to want to try that, so I'm going to recommend that you pause the video, you do the exact same thing I've done on this example, and then that you restart this to see if you're doing what I'm doing. I'm going to assume you've already done that, and I'm going to go ahead and talk my way through this. Again, I always rewrite the formula. I've already told you the 3 reasons for that. I know that this is already in standard form. If it wasn't in standard form, I would have to rearrange it and put it in standard form before I did anything else. And once it's in standard form, I know that my A is a 3, B is a negative 7, and C is a 2. That's the hardest part, because now I just plug in my numbers, perform a little bit of computation. 49 minus 24 is 25. This is cool because the square root of 25 is 5, so we get a rational number. If I wanted to solve this, I should have 2 solutions. 7 plus 5 is 12 divided by 6, which is 2. 7 minus 5 is 2 divided by 6, which is 1/3. And there's your 2 answers. This tells me, since these are both rational numbers, that this was actually factorable to begin with, which means if I had taken the time to try this using factoring, I would have gotten 3x and 1x. The signs are the same. They're both negative signs, minus and minus. And this has to be 2 and 1 or 1 and 2. I believe it's 1 and 2 equals 0. And of course, the zero product property says in order for that to be true, one of these has to be a 0. So either 3x minus 1 is a 0, or 1x minus 2 is a 0. And if we took the time to actually solve those, this left one would come out as 1/3, and this one would come out as positive 2. So there are multiple methods that you could use to solve this one. It's just a question if you want to take the time to try and factor that or not. Let's do another one. Again, I'm going to highly recommend that you pause the video, try this on your own, and then take a look at what I've done. I think that's going to be extremely helpful for you. I'm going to go ahead and keep working. Again, I always copy the formula. This is already in standard form. A is a -1, B is a +1, C is +1. I plug those numbers in. Be very careful about what happens with your negative signs. This -4 and -1 become a +4. A lot of times people will put a -4 here and they'll end up with 1 - 4. If you ever get a negative number under the radical, that just means you're not going to have any solutions. I add those together, I get -1 plus or minus radical 5. And then just one extra cool thing, if I were to divide this by -1, see this negative sign right here? Negative divided by negative would make that into a +1/2. And then if I were to take this positive divided by a negative, that would become a negative, and this negative would become a positive. Basically, this sign can become a positive, and then this sign stays the same. I'll let you think about that just a little bit. This positive became a negative, this negative became a positive, so it stayed the same. It's just a nice little way to simplify that just a little bit. Again, you're pausing the video as you try these, making sure that what you're doing is matching what I'm doing. Again, I'm going to do these just a little bit faster because you've paused the video along the way. A is 3, B is -4, and C is 8. And I plug those numbers in. I end up here, and I end up here. A lot of students freak out at this, and they really don't like it when I do this, but this is actually a really good thing for you as a student because you know that you cannot take the square root of a -80. That means as soon as I see the square root of -80, I know that this is going to have no real solutions. So it's actually easier for me as a student if this comes out as a negative number, because as soon as I see that, boom, I'm done with the problem. I just have to learn to recognize it. The one thing you have to be cautious about is, like we talked about on the previous problem, make sure your numbers here are correct, because you don't want to end up with a -96 and no solution when what you really meant was +96 and you would get a solution. So just be aware that you have to be very careful, particularly dealing with what your signs are when you're trying to add those together. This is a good point for good time for me to talk just very quickly about the discriminant. The discriminant is the term we apply to b squared minus 4ac. The discriminant helps us know how many solutions that we are going to have, because we know from our previous examples that if the number under the radical is positive, we get 2 solutions. If what was under here was a 0, 4 plus 0 and 4 minus 0 are both going to be the same thing, resulting in 1 solution. And then in this example, when you get the square root of a negative number, that doesn't make any sense. You get no real solutions. So if I were to just ask you how many solutions the quadratic equation 3x squared minus 4x plus 8 has, you really wouldn't need to use the entire quadratic formula. You could tell just by looking at b squared minus 4ac. If we had several days in class still to talk about this, I would talk a lot about the discriminant, but we are rushing to get things done this school year, so I'm not going to get much of an opportunity to do that with you. Just know it is important. It will come up again in Algebra 2. Here's one last example, I believe. Notice this one is not in standard form. It also has a random red bar in it that I need to take out. I'll deal with that later. Just know that to use the quadratic formula, you have to put this in standard form first, which means you need to multiply these together. That's polynomial multiplication. And then you need to move the 15 over to the left side. Notice now you have your ax squared plus bx plus c. Don't let it freak you out that they're not using an x, they've switched it to y. It does the exact same thing. So I write my formula. I remember what my standard form is, and I find my a, b, and c. And then again, I would recommend you pause the video and try the computations on your own. I'm going to keep going. I plug the numbers in, do a little computing, and I end up here. Now, a lot of people would accept this as a correct answer, and that's fine. Just keep in mind that you are dividing this by 2 and dividing this by 2. So you could go one step further and say 4 divided by 2 is 2, and 1 radical 57 divided by 2 radical 57 divided by 1 radical 57 divided by 2 is the same as multiplying by 1/2. So you could actually write it this way as well. Both of these ways are equally correct, but they're not always equally useful. It's just important for you to recognize that it could be either one, or that a book or another teacher or another mathematician might give you the problem in a different form than you're used to seeing. I know that got a little bit long. I do apologize for that, but it is extremely important that you have a solid foundation with the quadratic formula. Once you understand the formula, the actual work is not mathematically tedious if you have the formula memorized and you're careful with your positive and negative signs. I'm going to go ahead and end this, and I want to thank you all so much for taking the time to spend with us. I do wish you all the very, very best of luck. Make sure that if you got something out of this, you give me a big thumbs up, ring that bell to turn on your notifications so you can hear all about the new and exciting things coming out of Nunley Math. I wish you all the very best. You all take care of yourselves, all right? Bye-bye.